Welcome to lesson 7.1. In this lesson, you're building a production-ready customer support chatbot, not a toy demo, but something you could genuinely deploy. Project overview. Here's the scenario. An e-commerce company fielding over 10,000 support tickets every single day. Your job is to fine-tune a model that handles the common ones automatically, maintaining conversation context across multiple turns, and knowing when to hand off to a human agent. This is a 90-minute advanced project, and by the end of it, you'll have something portfolio-worthy. Project goals. The business case is compelling. A well-tuned support bot can reduce your team's workload by 60 to 80%, collapse response times from hours down to seconds, and generate annual savings anywhere from $100,000 to $500,000, while keeping customer satisfaction above a 4 out of 5 rating. Those business goals translate into 4 concrete technical targets. Resolution rate above 80%, meaning the bot handles at least 8 out of 10 queries without human involvement. Response time under 2 seconds. Context retention across 5 or more conversational turns. And escalation accuracy above 90%. The bot must correctly recognize when a situation is beyond its scope. These are your North Stars throughout the project. Phase 1. Problem definition. Gavins Puradiavans. Cookus Puradiavans. Cheese, you'll master these techniques quickly. Before writing a single line of training code, you need to understand what you're actually training for. Order status questions make up 35% of incoming tickets, the single biggest category. Returns and refunds account for another 25%. Product information queries sit at 20%, account issues at 10%, and shipping changes at the remaining 10%. Now layer in complexity. 60% of tickets are simple. One question, one answer, no prior context needed. 30% are medium complexity, requiring 2 or 3 conversational turns. And 10% are genuinely complex, sensitive situations that need a human. That 10% is where your escalation logic earns its keep. Here's the Python dictionary that codifies those targets as measurable metrics. Resolution rate is set to 80%. That's your primary KPI. Average response time is capped at 2 seconds, which is the threshold where users start perceiving a system as slow. Customer satisfaction targets a 4 out of 5. Escalation precision is 90%. Meaning 9 out of 10 escalation decisions should be correct. And average conversation turn sits at 3.5, which tells you how efficiently the bot reaches resolution. These numbers aren't arbitrary, they're what separates a chatbot that helps from one that frustrates. Keep them visible as you train and evaluate. Phase 2. Data collection. Fiscus. World master these techniques quickly. Your best data source is historical support tickets, real conversations between real customers and real agents. This code loads that ticket history from a CSV file into a pandas data frame. The first print statement gives you the total ticket count, which tells you immediately whether you have enough data to work with. The second shows you the column names. Confirm you're seeing fields like ticket ID, customer message, agent response, and category. If any of those are missing, your conversion step later will need adjustment. The sample ticket at the end is your sanity check. Read it and ask whether it looks like the kind of conversation you want your model to learn from. If you don't have proprietary ticket data, the Betext customer support dataset on Hugging Face is an excellent starting point. The load underscore dataset call fetches it directly, no manual downloading required. The first print confirms how many training examples are available, and the second shows you a sample entry. Pay attention to the structure of that sample, the field names, the format of the instructions and responses. Your training pipeline needs to match this structure exactly, so understanding it now saves debugging time later. When real ticket data is scarce, Synthetic generation fills the gap. This function calls GPT-4 with a carefully constructed prompt that specifies the conversation category, the complexity level, and realistic details like order numbers and product names. The temperature of 0.7 is deliberate, low enough to keep responses coherent and on topic, high enough to introduce the natural variation you'd see in real customer language. The loop generates 100 conversations per category, and the final print confirms your total synthetic count. Treat synthetic data as a supplement, not a replacement. Blend it with real examples whenever possible. Raw tickets need to be reshaped into chat format before the model can learn from them. The convert underscore to underscore chat underscore format function takes each ticket and structures it as a sequence of messages with explicit role labels: system, user, and assistant. This matters because the model was pre-trained on this exact structure, and deviating from it will hurt performance. The code processes up to 1,000 tickets, then splits them 80-20 into training and validation sets. That validation split is critical. It's your early warning system during training. Both sets are saved as JSON-L files, which is the standard format for this kind of sequential data. The final print confirms your exact counts before you move on. Phase 3. Model training. This is the core of the project. The model is unsloth/lama-3.2-3b-instruct 3 billion parameters, instruction tuned, loaded in 4-bit precision to fit comfortably within your P40. The maximum sequence length of 2048 tokens accommodates multi-turn conversations without truncating context mid-dialogue. After loading, a chat template is applied to the tokenizer so it correctly formats the system, user, and assistant turns. LoRa is then added to the model. This is what makes fine-tuning feasible on a single GPU. Instead of updating all 3 billion parameters, LoRa inserts small trainable matrices into the attention layers, reducing the parameter count that needs gradients by roughly 95%. The training configuration sets epochs, batch size, and learning rate. Then the trainer runs against your JSON-L files. When training completes, both the model and tokenizer are saved to disk. That save checkpoint is what every subsequent phase depends on. Phase 4. Evaluation. Before running evaluation, you need a test suite that covers the full range of scenarios your bot will face in production. Each test case specifies the inquiry category, the exact user message, what information the bot should extract or provide, and whether the situation warrants escalation. Notice the should_escalate flag. This is how you'll measure escalation accuracy separately from general response quality. A test case involving a complaint about a damaged item, for example, should trigger escalation. An order status query should not. Running the bot against these cases gives you ground truth numbers, not impressions. The evaluate_bot function loads your train checkpoint, same 4-bit loading as training, same tokenizer, and runs every test case through the model. For each case, it generates a response, checks whether the expected information appears in that response, and records whether escalation was triggered. The time.time SA calls around each inference measure latency precisely. After all cases are processed, you get 4 numbers: response accuracy, escalation accuracy, and average response time. Your targets are 80% response accuracy, 90% escalation accuracy, and under 2 seconds per response. If any of those fall short, the results JSON gives you the raw data to diagnose why, which categories failed, which escalation decisions were wrong, and where latency is spiking. Phase 5. Deployment. 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 The deployment layer is a fast API service that wraps your trained model. On startup, the model and tokenizer are loaded from your saved checkpoint directory, the same 4-bit configuration from training. Fast API's data models define the exact shape of incoming requests and outgoing responses, which means any malformed payload gets rejected before it ever reaches the model. The chat endpoint receives a user message, formats it with the chat template, runs inference, checks the response for escalation signals, and returns a structured JSON reply. The metrics endpoint exposes request count and average response time, which you'll use in phase 6. When the server starts, you'll see a confirmation in the terminal. That's your signal that the model loaded cleanly and the API is accepting connections. Navigate to your deployment directory and start the server with these 2 commands. The directory change ensures Python resolves all relative paths correctly. Your model checkpoint, any config files, all of it. When app.py starts, watch the terminal output for 2 things: the model loading confirmation and the UVCon startup message showing the host and port. If you see an error instead, it's almost always either a missing dependency or an incorrect model path in your configuration. With the server running, this curl command sends a live test request, a simulated customer asking about order number 1, 2, 3, 4, 5. The content type header tells the server to pass the body as JSON. The response you get back should be a JSON object containing the bot's reply. This is your first end-to-end confirmation that the entire pipeline works. Data in, response out, through the API. If the response looks coherent and addresses the order status question, your deployment is functioning correctly. Phase 6. Monitoring and iteration. A deployed model that never improves is a model that slowly degrades in usefulness. This feedback endpoint is what closes the loop. The feedback model captures 3 things: the ID of the response being rated, a boolean indicating whether it was helpful, and an optional free text comment. Every submission is appended to feedback_log.jsonl, 1 JSON object per line. That file becomes your continuous stream of ground truth from real users. The acknowledgement response back to the client is a small but important UX detail. It confirms the feedback was received, which encourages users to keep submitting it. This analysis code reads your accumulated feedback log and surfaces 2 things immediately. First, the helpfulness rate, the percentage of responses users marked as helpful. This is your real-world resolution rate, and it should trend toward or above 80% over time. Second, the unhelpful responses filtered out of the data frame, grouped by the issues users reported. These clusters tell you exactly which query types the model is still struggling with. That list of failure patterns is your input to the next training iteration. Here's how you feed those failure patterns back into the model. For each unhelpful response, you pair the original user query with a manually corrected answer, the response the bot should have given. These pairs are formatted into the same chat format dictionary structure used in phase 2, then appended to your existing train.jsonl file. Opening the file in append mode is critical. You're adding to the dataset, not replacing it. After this step, rerun the training process from phase 3. The model will now see both the original examples and the hard cases it previously got wrong. This is the iteration loop that takes a good chatbot and makes it a great one. Project completion checklist. Success. Here are the numbers from a completed run of this project. Resolution rate 82%. That's above the 80% target. Average response time 1.5 seconds, well under the 2-second ceiling. Escalation accuracy 92%. Clearing the 90% bar. The production API is live and the feedback loop is collecting data for the next iteration. Every one of these targets was met on the first training run, which tells you the architecture and data pipeline are solid. Next project. The support bot is complete and production ready. The next lesson takes a different angle. Instead of answering customer questions, You'll train a model to generate code documentation automatically. That's lesson 7.2, Code Documentation Generator. Additional resources. It's a Veracity. The resources linked with this lesson cover Chatbot best practices, fast API deployment patterns, and the customer support metrics that matter most in production environments. This project is genuinely portfolio ready. It demonstrates data preparation, fine-tuning, API deployment, and a live monitoring loop, all in one cohesive system. This diagram shows the full request pipeline your chatbot runs on every message. A user message enters the system and hits the intent classifier first. This component determines what the user actually wants before anything else happens. That classified intent then queries the knowledge base, which holds your FAQs and common support answers. The result feeds into your fine-tuned language model, which generates a conversational response grounded in that retrieved context. Before the response reaches the user, it passes through a safety filter that screens for inappropriate or harmful content. Every component in this chain has a distinct job, and understanding the boundaries between them is what lets you debug and improve each one independently. This chart shows intent classification accuracy broken down by category after fine-tuning. The most important number here is at the top. Escalation to human achieves 98% accuracy. That's the category where mistakes are most costly. A missed escalation means a frustrated customer gets no real help. Account reset follows at 96%, billing query at 94%, tech support at 91%, and product info at 89%. Complaint handling sits at 87%, and general chat at 82%. Those bottom two categories are where you'd focus your next round of data collection. More varied complaint examples and more casual conversation samples would push those numbers up meaningfully. This diagram illustrates the retrieval augmented generation pipeline, the mechanism that gives your chatbot accurate, grounded answers rather than hallucinated ones. The user's query is first converted into a vector embedding using a sentence transformer. That embedding is compared against a vector database of FAQs and past support tickets, and the top three most semantically similar entries are retrieved. Those entries are combined with the original query to form a prompt, and that prompt is what gets passed to the language model. The model never has to rely purely on its parametric memory. It has relevant context in front of it every time. This architecture is why the chatbot can answer specific questions about your product catalog without retraining every time something changes. This before and after chart makes the impact of fine-tuning concrete. The orange bars are baseline performance, the pre-trained model with no domain adaptation. The green bars are post-fine-tuning. Resolution rate and customer satisfaction score both jump from below 50 to near or above 80. Escalation rate drops, which means the bot is handling more queries directly rather than punting them to human agents. Average handle time improves as well. Queries get resolved faster. The pattern across all 5 metrics tells a consistent story. The pre-trained model has the language capability, but fine-tuning on domain-specific data is what makes it actually useful for customer support. That's the core argument for everything you've built in this lesson.